Back in March of 2023, in a laboratory with no cell phone service and a need in the community for computational legacy data, these students, under the direction of this professor, tested the aerodynamics of a cow at Mach 7 for science.
What was the silliest thing that you put in the wind tunnel?
Oh yeah.
Silliest thing, okay.
Let's talk about
The cow. The cow was a lot of fun.
Holy cow, what happened?
Holy cow, right? So Dr. Combs at some point during a team meeting brought up the idea of putting a cow in the wind tunnel. No science behind it, or some science maybe, but really just for fun. And we kind of made it happen. So I went to Tractor Supply and bought a cow from there, put it in the vise that we've got over there, and just kind of drilled into its backside. And me and a few other undergrads mounted it up, ran the test, and it came out looking really cool. And
Yeah.
got some good internet attention too, which was really fun. But
What did we learn from that test? Like, really, what can we do with that information?
well, I'm trying to think. So with that kind of information generally, it's really helpful, right? Because we can see with the Schlieren imaging, and if you have the video in the video of the cow
Yes.
uploaded in this, you can see the shockwave structures, which is really helpful when we're doing more scientific tests. Now I will say, you never know when we might need to send a cow at Mach 7, right? Like maybe the aliens are invading and we figure out that the only thing that can penetrate the mothership is a cow. And we've got to make it happen.
dairy.
And this study will be like the thing that saves us.
This may seem like a fun experiment, but wind tunnel testing is no joke.
Any second. All right.
Yeah.
That was perfect timing. What the heck? Hey guys, so I just got to San Antonio and I'm going to be interviewing Dr. Chris Combs, who I met at the SciTech convention back in January. He is an expert in hypersonics. He's definitely interested in what's going on with Starship, and we are going to get a demonstration here at UT San Antonio of the wind tunnel. So let's check it out.
UTSA unveiled their state-of-the-art research facility in 2021 with a Mach 7 tube wind tunnel. This took 3 years of construction to complete, and it's 50 feet long and weighs more than 7,000 pounds. I got to take a tour of the UTSA Hypersonics lab under the direction of Dr. Chris Combs. So this wind tunnel can conduct a variety of tests under Mach 7 conditions, which is equivalent to traveling over 5,000 miles per hour at sea level. And this type of wind tunnel is rare. It's only available at a select number of American universities, in addition to a few in operation at the Department of Defense, NASA, and national lab facilities. The $1.5 million investment in the Mach 7 facility makes UT San Antonio increasingly competitive to secure projects from the Department of Defense, NASA, and other governmental agencies. The lab can conduct multiple tests per day with low overhead costs. This makes it an attractive place for aerospace-related businesses to test and validate various models under extreme hypersonic test conditions.
We've got computational models on one hand that can give us information we're not going to get from anywhere else, because you've got this 3D virtual environment. You can pick any variable anywhere that you want. It's amazing things that we can do with computational fluid dynamics right now, but they're still models, and there's gaps in those models, and they're not perfect, and depending on how much investment you put into that, how long you're willing to let that thing run on how many supercomputers, those answers aren't always just right. And so you need to validate that with wind tunnel testing, with ground test campaigns. There's places like our tunnel that are relatively cheap as far as wind tunnels go, and students are able to run them. And then you look at other places, the larger scale facilities, maybe where you get a higher temperature that's closer to flight, they're gonna start to get more expensive, all right? You're gonna have year-long plus wait times to get in those tunnels.
Wow.
And then you have flight test, which, even a flight test on a sounding rocket might be $10 million, okay? You can build your own wind tunnel for the cost of a lot of flight tests and cheap flight tests. So that's something that you want to do, but how many of those can you afford? And if the flight test doesn't work, can your program survive that? That's always a question that people have to ask themselves, and you better learn a lot from your flight test, successful or not, right? So you better instrument that thing as much as you can, collect as much data as you can. But at the end of the day, there's things that you will see in a wind tunnel that you can't see in flight. It's kind of like another step. It's the same type of step we make from computational world to wind tunnels, and the type of things that we can see and measurements we can make
Right.
and data we can get, it's a similar jump to flight test, because it's so hard. You're not there in a lab with all your instruments pointed at this thing. That thing's flying fast. And so there's challenges in getting data with a flight test, and then obviously there's various scales of flight test, from like smaller subcomponent thing to full scale flight vehicles.
Right.
And SpaceX tends to seem to jump right to the last step of that, for better or worse.
Yeah.
When it works and it's awesome. When it doesn't work, you hope that they learned a lot.
I gave an early release of this video to my patrons to get some feedback, and one of my patrons said, "Boy, what a great video, but this really made my head hurt. This could be a great opportunity to take the classical mechanics course on Brilliant." If you enjoyed watching this video, but maybe you want this topic broken down a little bit more, check out this course on Brilliant. In the course, you'll establish the bedrock principles of physics and use them to reveal matter in motion, from drones and rockets to skyscrapers and blinking fireflies. By the end, you'll develop a rigorous approach to describing the natural world, and you'll be ready to take on new challenges in quantum mechanics and special relativity. Some of the topics covered include forces, kinetic energy, momentum, Newton's laws, oscillations, potential energy, projectile motion, the rocket equation, and static equilibrium. So if you don't have the time or money to become a student all over again, you can get started learning about this for free on Brilliant. In fact, Brilliant is the best way to learn math, data science, and computer science interactively. On Brilliant, there are thousands of lessons from basics to advanced topics, and new lessons are added every month. To try everything that Brilliant has to offer for free for a full 30 days, visit brilliant.org/EllieInSpace, or you can click on the link in the description. The first 200 of you will get 20% off of Brilliant's annual premium subscription.
Ellie in Space here, joined by Dr. Chris Combs. Many of you met him in January when I interviewed you pre-Starship launch at the SciTech Forum. And now I live in Texas. You live here in Texas.
So much has happened, yeah.
So much has happened. And so I thought that it would be cool to kind of see, you were talking about your wind tunnel. A lot of people have interest in seeing how that works, and just chat with you about all the things that have happened and kind of what you're researching right now.
Yeah, absolutely. So you want to hear about what this thing is and what we got going on down here?
Yes, because I have no idea what's what.
Yeah, all right, cool. So let me start off just kind of a basic overview of what we're doing and why we care about this. So this is a Mach 7 hypersonic wind tunnel that we built here at UTSA in San Antonio. The reason that we're interested in something like hypersonics is because, so we're talking about velocities a mile per second and faster, really. So things that go really fast. And it's a pretty relevant flight regime for a lot of problems that people care about, all right? So space flight, that's an obvious one, right? You're looking at anything that's up in orbit, up in space, is really going about Mach 25 plus, okay? So like 25 times faster than the speed of sound. So yeah, you're cooking, right? That's about 90 minutes to make an orbit. And then it's not really the hypersonic aerodynamics that we care about. They're not really an issue when you're out in space. There aren't enough molecules to interact with for it to be a problem. But as soon as you start to come back down, then you're dealing with that issue. All right. If you want to go to another planet like Mars, you're dealing with hypersonic aero on the way in. And also a lot of these rockets are even dealing with hypersonic problem on the way up out of the atmosphere. You can hit Mach 5 a few minutes into flight. I like to remind people that there's no flash of green light when you hit Mach 5. That's kind of a textbook number that we use because it's convenient and a nice round figure. But when we talk about hypersonics, really it's not just about a definition of Mach number. It's about what happens in terms of the aerodynamics and the design considerations that you have. Because when you get into that type of speed regime, you're punching into the air so fast. Some pretty extreme things start to happen because already once you're going faster than the speed of sound, the air molecules, they don't have time to get out of the way. That's why shock waves form, all right? Because you move your hand through the air right now, and the air around your hand as it's coming, they're like, hey guys, there's a hand, move out of the way, right? You hit Mach 1, and now those molecules can't communicate with each other anymore. All right, so then what happens is they all just get piled up on this thing that's just plowing through, and it creates a shock wave. to accommodate for that. Now, you start doing that at, getting close to Mach 5 and Mach 5 plus, you're hitting those air molecules so hard, you're creating incredible amounts of compressive heating. The air is ripping by, causing frictional heating. You can hit the molecules so hard that you actually rip them apart. So the O2 and the N2 that's normally in the air, you can dissociate those molecules, and now you have O atom and N atom floating around. But they like to recombine, and so they come back into other things like NO. All right, all kinds of funky chemistry starts to happen. It's not really air anymore. You can generate like a plasma shield that forms around your vehicle.
Oh,
it's
wow.
basically like it's on fire almost, and you're looking at temperatures that get generated that are comparable to the surface of the sun. So you get to a place where we really probably more cleanly define hypersonics. It's not about Mach number, but it's about the point where your vehicle design is dominated by dealing with the aerothermal effects that are going on. All right, that's more important than like big fat wings that generate lift. It's what do we make that's survivable?
Yeah.
What do we make that can actually go that fast too? Rockets can do that for you. Rockets aren't perfect. There are issues with rockets at times. And then, are there air breathing systems? Are there things with higher ISP that we can get away with? And I know this is like a space channel, but the space folks should, if they're not, they should be thinking about rotating detonation engines and air breathing propulsion and scramjets and things like that, because maybe that's a cool first stage that saves you some weight.
You heard it here first.
People are talking about that as a Mars thing, right? So, it's not totally crazy. But, and there's defense reasons that we're interested in hypersonics that are obvious in the news. There's commercial flight reasons. You look at the places that are developing, high-speed vehicles that could get you across the country in 30 minutes or something like that. You can go from San Antonio to anywhere in the continental U.S. in 20 minutes at Mach 7.
Wow.
Right? So you could, hop on a plane from Austin, go have dinner in New York, get home in time for the 10 o'clock news.
Oh my
right?
gosh.
That'd be cool, right?
That no one watches anymore.
Yeah,
by
so
the way, but.
that's what we're working on. Or watch the latest Alien Space video.
Okay,
right?
that's better. And that's what we're thinking about, eventually with the Starship point-to-point concept. At least
Yeah.
that's what was touted really in the beginning.
Exactly, so that type of stuff. The way that we are tackling this challenge and trying to study this really extreme environment is with this wind tunnel. So we built it. It took us about 3 years to build this thing. We finished in spring 2021.
Wow.
And this is test, it looks like 522 that we're about to run.
Okay, so as we can see, there's the number
So
on
that's
it.
our diaphragm that I believe is going in there,
Wow.
right? Yeah.
So wow.
Yeah, so in 2 years, we've done that many.
Okay. So you're not using it every day?
Yeah, when we're running full bore, we can turn this over in 30 minutes or so, and cadence 4 to 6 times a day isn't crazy, but because of the type of work that we do, we probably spend more time tinkering with the measurements and the experimental setup than just like waiting on the tunnel to be ready to run. So we haven't been really rate limited by the tunnel. It's more about the complexity of the experimental setups that we're going after. Right?
Well, our generous cameraman, Joe Tagmeyer, has a question for you.
Yeah, we just looked at this plate here, and you said it was test 522. Do you have any examples of what this plate looks like after the test that you could show the audience?
Yeah, absolutely. And I'm gonna do that as I talk through how this tunnel operates, which I think we're ready for.
Yeah.
So this is, compared to even some low-speed tunnels, mechanically pretty simple. All right, because really at its purest form, this is high pressure on this end, low pressure down here, separated by our diaphragm burst disc, and then with a converging diverging nozzle that does all the magic there. That's really what we have going on. All right, so this is rated for pressures up to 2,400 PSI, so you're like 100 times car tire pressure. All right, It's scary pressure. I tell my students, if you're not scared of this type of pressure, you don't belong in this lab because there's something wrong with you. You're going to get somebody killed. All right. On the low pressure end, we can pull down to about 1% of atmosphere. And we separate that with our diaphragm, okay, which gets installed in here. The students actually make these. They machine them, and this is an aluminum one. We have different thickness, different scoring patterns that we use depending on what pressure we want to burst at. And then the idea is that once you get to the pressure you want, this thing pops open.
Whoa.
in about 10 milliseconds.
Wow.
So you can take a peek at that. It's sharp. We don't deburr these, but
Yeah, that looks really sharp.
yeah. So and this petals and opens up, and these petals generally stick along the inside of this. And we keep all of these in case we notice something weird in the data. We can
Right.
go back even years later and check out the diaphragm and say, hey, did something weird happen with that one that might have caused us to see this? But yeah, so that diaphragm pops. That allows all this high pressure air to rush into our plenum or stagnation chamber. And you design this so that in this section where it widens out, the flow velocity is basically 0. Right? This is Mach less than 0.03 in here. So this is just really high pressure air reservoir that's just sitting there, and it feeds into our nozzle, which is right here. And so notice this is a kind of happy accident O-ring contour that ended up on the outside of our nozzle. This is about 2,500 pounds of stainless steel right here. That shape should look familiar. That looks like a rocket nozzle, right?
Yeah.
It's exactly the same concept, the same physics. So what you do is this air comes in subsonic, very, very slow, all right? You crunch that down to make it go faster. It's a principle that probably a lot of people have had experience with. It's like if you're watering your plants outside or watering your car, you put your thumb over the hose bib, makes the water go faster, right?
Yes.
It's just simple conservation of mass. There's less area, same amount of stuff has to go through, so it goes
Right.
faster.
Interesting.
All right?
Okay.
You can crunch air down enough in a small enough little slot there where it actually hits Mach 1. It's moving at the speed of sound. And so in air, it's around 1,000 feet per second, right? It's like the length of a par 4 in 1 second. So if you're standing on the green of a par 4 at the pin, all right, and then you saw somebody swing and hit their driver, you'd see them hit it, and it would be pretty much 1 second after they actually hit the ball when you would hear the ping. That's the speed of sound. That's Mach 1. And so when you get to this point, all right, that hits Mach 1, it's called choking the flow. You can't accelerate faster than Mach 1 by converging, all right? That's your limit. So then what you have to do, the physics actually change a little bit because the molecules can't communicate forward anymore like they used to. Start acting a little bit more like traffic on I-35, all right? And I know that you're new down here,
Yeah.
and people will try and make you feel differently, those big trucks, but they cannot make the person in front of them drive faster no matter how hard they try, all right? It works the same way in supersonic flow. So you start to expand the air out,
Right.
they can't push the molecules faster, so it's the same type of dynamic. What happens on I-35 when they crunch it down to 1 or 2 lanes? Everybody stops,
Yeah.
right? Everything slows down. So what you do to make things go faster, you add lanes, expand things out. Okay, there's a segment of like traffic Twitter that's going to get really mad at me for saying that, but that's the way that it works. Add more lanes, people spread out, they start going faster, and so we accelerate this out to Mach 7.
Okay.
All right, that was our design condition. A question I get a lot, there's kind of 2 that usually come up right here. 1, why Mach 7? You could expand this thing out, you could hit Mach 25,
Yeah.
right? Nothing in science comes for free, right? And I'm not talking about monetary cost, I'm talking about physics cost.
Right.
So there's a price for expanding the air out and accelerating it. All the energy that was in those air molecules in the temperature and pressure terms is now in momentum. So what happens is as you expand, you accelerate, you start going faster, but pressure, temperature both plummet, all right? So the air that's coming out of there is like cryogenically cold. It's not really representative of even upper atmosphere
Right.
anymore. And it's pretty low pressure. So, and then the more you expand that out, that really goes almost like squared, all right, as Mach number squared. So it just gets worse and worse and worse. So higher Mach number, things get really, really cold to the point where you're liquefying the air molecules, all right, which that's not the kind of test that you want. You've got pressures that just aren't meaningful at all. So Mach 7 was kind of what we were able to design for with the materials that we had, and it made sense. The other question people say is, well, why don't you just, add more pressure, make the air go faster, increase the Mach number? It's counterintuitive, but actually the physics of like converging, diverging nozzles and wind tunnels, your Mach number is determined by the expansion ratio in the nozzle, not the back pressure ratio. Once you hit the pressure ratio that starts the nozzle, adding more back pressure doesn't increase your Mach number on the other end. It just increases your mass flow rate, all right? It increases the pressure down there and your effective altitude, or a thing we call Reynolds number, but it's not going to change the Mach number. So we're really limited by just the shape of the nozzle contour that we have. So if we want to change the Mach number, we can change the contour and put a new nozzle block in. All right, that's one way to do it. But there's another trick. We've done this before. You can play a little game by changing the test gas. All right, so there's this thing called ratio of specific heats, or gamma, in my world, that if you use a gas with a different gamma than air, it's about 1.4, and you can use something like helium, for example, that's a lighter gas, has a different gamma, then you get a different Mach number when it comes out. So you can use helium, and you get about Mach 11 with this nozzle.
Oh, wow.
All right, so we've done that before too, and that's fun. And that kind of leads me to another thing that's really relevant to space that we are able to do. What's unique about this tunnel is while we usually run with air, and we're going to run with air today, really anything that comes in a gas bottle, we can, in theory, put in this and use as our test gas. All right, so if we want to do a Mars atmosphere, we can totally do that. If we want to, do some funky stuff with chemistry, if we wanted to do some exoplanet or something, there's ways that we can do that type of stuff.
And this research isn't just for the students. I mean, you're helping, you were saying NASA, for example, so this is being used practically, right?
Yeah, I mean, we've got funding from NASA, from Air Force, from various DoD agencies, from industry. So,
what about the private space companies? Are you pretty involved with them or not yet?
A little bit. It's something that we're working on. Something that I have noticed, people can jump in the comments and correct me if I'm wrong, SpaceX isn't doing a lot of foundational research. It's very, very applied. They kind of know what they want to do, and they're focused on, we're going to make this one piece of tech work for what we're going to do. The thing is, for a lot of research like this, you're looking at long lead outs before you see the impact. So we're working on problems that are going to be solved 15, 20 years from now, not 6 months from now.
Right.
So that's not to say that there aren't academic, there aren't things that we can do that have a short-term impact, but I haven't seen SpaceX a lot of investment in university type research. But we are, the way that we contribute is we're training students with the skill set that people need.
Right.
Because and you made the comment about how the research we do contributes, which is important, and we're kind of trying to walk a fine line between having a facility that's accessible for students, where they can learn, where they can feel free to make mistakes, and where they're challenged, but at the same time, where we are doing research that's pushing state of the art.
Right.
And so we do both at the same time. And we're definitely performing for sponsors and funding agencies while the students are getting trained, which is great.
How many of these are there in the country?
Yeah, so there's about 24 sites in the U.S. that are doing hypersonic ground test. Of those, 12 or 13 are at universities.
Okay.
All right.
So
there's maybe 5 or 6 of us that are universities in the United States that can do Mach 7+ on campus.
wow.
It's a very, very small group.
This is a rare treat that we get to see here today.
Yeah.
That's awesome.
And so, and like I was saying, a lot of what we do is pushing state of the art in the measurement capability with lasers, cameras, optics, coming up with new ways to make these measurements that then can be translated to industry and government partners.
Right.
So that's a big part of what we do. But the students really, they have a lot on their plate, and that's why they come out with such an important skill set, because all of this was student driven. All the wiring and the plumbing.
It's a lot of wiring.
They did that,
oh my
right?
gosh.
I mean, this is 5 years worth of work that you're seeing now,
Wow.
because there's always new stuff to add in. There's always little changes being made, but they routed the plumbing and the wiring. They set up the wind tunnel test. They machined the diaphragms. They install the diaphragms.
And so here
they
at
set
the
up
end,
the optics. Yeah.
what is this?
So this is where we put the misbehaving students.
no.
But so this is our 1,600 gallon vacuum tank, and so this is really just like a vacuum reservoir, because the air needs somewhere to go during the test to maintain condition. And so really that's what's going on, is the air is rushing through here. This is our test section. It's about 8 inch by 8 inch, and then the air rushes through into the vacuum tank. So some people that don't have wind tunnel experience, they see like an 8 inch by 8 inch test section, and they're like, oh, that's kind of small. There's no hypersonic wind tunnel in the world that does full-scale vehicle test. That just doesn't exist. in large part because of some of those trades that I was talking about
Right.
with, nozzle size. So you've got places like the 8-foot high temperature tunnel at NASA that are really, remarkable world-class facilities, but there just aren't very many of those. And then, it's hard to get somebody to invest hundreds of millions of dollars in a new wind tunnel.
That's
all
a
right?
deep echo.
Yeah. I mean, because it runs all the way through there. This whole
so
thing is
cool.
closed in. Yeah. Yeah. And so what we do, we use scaling relationships and our knowledge of fluid mechanics to, run scale models and still get information that's relevant. And that's how pretty much all wind tunnels operate.
Yeah.
So there's no like full-scale flight test that happens at the wind tunnel stage.
Okay.
But we 3D print little models. We can make any shape that we want,
Right.
any geometry that we want, and as long as it's really about 3-inch diameter cross section or less, we can probably run it.
Well, it sounds like we might get to see a demonstration today.
Yeah.
So what are we going to see?
So in real time, you're not going to see much. For
Okay.
one, we're not going to be here. We're going to be in there. All right.
Okay.
And so if you want to pop your head in here.
Yeah. Interesting.
So this is like mission control for us.
Yeah, I like it.
And because, in large part, this is a student facility, I mean, safety is really important, right? So as soon as we start to pressurize, no one's in the lab. So we station people outside the doors to make sure, nobody wanders up wondering what's going on. And then everybody running the test is in here. And so you control everything from in here, the heaters, the vacuum pump, the compressor, all of it. We've got eyes on the experiment from in there, and then we've got the experiments and the cameras. They'll be up on screens in here as well. So you come in here, what's going to happen when the test actually initiates? So we have like 50 to 100 milliseconds of steady state Mach 7
wow.
flow. Right, so it's quick.
Really
now
quick.
at Mach 7, that's a long time, especially when you can image at like 1 million frames per second, which is a lot of what we do. So we get gigabytes of data every shot, plenty of stuff for an aerodynamic standpoint. But it's an impulse facility. We get a short little burst of air, and then we set up again.
Okay.
All right. So it's kind of like a metallic balloon being let out type of sound that you'll hear. You might notice a small change in like the object because we're doing a free flight test. The object's not going to be sitting there anymore.
Right.
But that's going to happen in like the blink of an eye
Yeah.
on a single frame. So it's going to happen and it's going to be okay.
So
Well, yeah.
yeah.
That was the run. And then what we do is we go back and we can look on it on a high-speed video. And then, when you play that high-speed video back at 30 frames per second,
Yeah.
it's like a 20-minute video, right?
Wow.
Yes. I mean, you'll fall asleep watching it because there's
gosh.
so much information there. But in the moment, your physical presence is going to be boom.
Right.
And that was
Right.
it. Because it really is. It's the diaphragm bursts, that air rushes through, and that's what we've got. And then we've got, like I said, we've got the eyes on with CCTV. If anything really bad happened, we
Right.
would know before we walked out there so we don't get surprised by something.
And it looks like they're kind of setting up, finishing touches.
Yeah, they're setting up. They're bolting everything together. They're going to install that diaphragm pretty soon. And then once the diaphragm goes in, we're probably 30 minutes away.
30 minutes? Okay.
Yeah.
Cool.
Oh.
So we're getting ready for the test.
Yeah. So we're watching the pressure pull down. We're kind of making a sort of trade-off call on like how long we want to sit here and how long we want to let that pressure drop. Because the more pressure ratio you get, you get a little bit longer runtime. You might get a little bit cleaner burst. If you don't wait long enough, you run the risk of the tunnel not starting, and so you don't really get to Mach 7 in the test section. But we're probably fine, but we're gonna see.
Okay.
It's a situation where like the worst case scenario of it not really hitting Mach 7 is not that big a deal for what we're trying to do.
Okay.
Yeah.
So where should I just be looking, like in that little box basically?
That's like, yeah, and it's like washed out because of the light, so you're
Yeah.
really not going to see anything.
Not
but
gonna see it. I'll hear it.
you'll hear it.
I'll hear
If you
something.
see anything, you'll see it. You might notice it recoil a little bit, like it'll shake some.
Okay. Shake something.
It should get over 200 psi. Then you start to get into like Jack in the Box mode.
Right.
If it gets up to like 300 and it still hasn't popped, we might abort. This is a type of thing where we're kind of trying to demonstrate a technique that not really anybody's been crazy enough to try. What she's working towards is getting pressure sensitive paint on a ball that's flying in the wind tunnel and turning that into pressure data while it's in flight.
Oh, okay.
So
Sounds
it's
complicated.
like, yeah, it's super complicated. There's a reason nobody's done it.
So
So
who's
he's
that?
talking to people outside.
Okay.
We have people out in the hallway now to make sure that nobody walks up
Oh,
right when it pops, right?
why? What would it? I mean.
Well, you wouldn't want somebody to like try and come into the lab right
Oh my
as
gosh!
it's
Yeah.
happening,
Lock the
right?
door.
Yeah, so we've got, and we actually, with that thing, we lock out the card swipes too.
Okay.
But
good.
still, we wouldn't want to risk like some curious student like
Some weird. Yeah.
poking in the window, right? Yeah.
So, like, if you were in there right now when it happened, what happens to you?
You'd probably be fine. You'd want the ear protection on.
It would just hurt your ears.
Yeah,
Okay.
but
Didn't startle me.
the real reason why we don't want people in there is in a worst case, if something like, as we pressurized, if something went catastrophically wrong, like that pipe is a bomb.
Yeah.
So
How
in
safe
here-
is it in here?
Yeah, I mean, we've got a bunch of stainless steel and a reinforced wall in between us, so we're good in here.
Okay.
All right.
It sounds like Starship launch.
Yeah, right.
I was so scared because I was still in crutches.
Yeah.
And I'm like, I can't, they're like, just make sure to be able to run and duck and cut. I'm
Yeah.
like, I can't run, guys.
All right, we're at 250, so it's like any second now.
Any
this could
second.
happen.
All right.
Yeah.
That was perfect timing. What the heck?
That was it.
Oh my gosh.
What you expected?
No.
It's a sound that's hard to explain to people. You just until you've heard
Yeah.
it.
It
But
sounds like it's breathing at the end. I definitely did the like nervous shaky hand. Okay.
All right, so you want to do the all clear, Angie, and then we can go in there and see the video. Our little release mechanism went down inside the floor, just like it's supposed to, and now we've got high-speed data. That's a ball in flight at Mach 7. And so Sophia's going to use that and do some object tracking and get some practice on her code. And then the next step is going to be to put some paint on it.
What did you say the frame rate was for this image?
Was that 40K?
Yeah.
Yeah, 40,000 frames per second. And your iPhone slow-mo is probably 120. And this is kind of what I was saying. It's like 50 milliseconds sounds like a pretty short time, but then you watch the videos and you're like, oh my God, this thing
Yeah.
takes forever. So at 40,000 frames per second, that's, it's a long video. It's falling at the rate that gravity lets it fall.
Oh my gosh. So we're watching it fall right now.
Yeah, it's just,
What?
that's one of the fun things about the free flight testing and hypersonics. Like, we don't really include a gravity term in really anything that we do because it's working so slow compared to the aero. We're not really concerned about it.
Aerospace engineering is notoriously the hardest major in college to get into because of the amount of math and physics required. Aerospace engineers need to be able to think creatively and solve problems on their own, as well as work in a team setting. Here's a little interview I did with one of the talented minds in the lab.
What made you want to study this in particular?
So to be honest, I heard about it at a dinner I went to with a person who had worked here before, and initially I just thought it sounded awesome, which I still think it does.
Yeah.
But I emailed Dr. Combs pretty much and had the expectation of just maybe letting him know my name, get my foot in the door, but he actually decided to let me work here, which is really cool. So I love the work. I feel like it's really, you get to be creative, you get to problem solve. It's the stuff that I've been wanting to do since I was like a kid and kind of wanted to do engineering. So it's really cool to be actually doing it, especially so early. Not what I was expecting.
How old are
definitely.
you?
I'm 19.
Oh my gosh, that's awesome. What is like your dream, or where do you see yourself?
That's a good question.
5 years.
That's a good question. It would be really cool to be doing this kind of stuff. I think I do want to go to some kind of grad school. Ultimately, I think the ideal would be to work on some kind of rocket technology, probably engines, or maybe like scramjet engines or something. That being said, I'm just a sophomore, so like I don't know what I'm doing with my life.
I'm fully confident you can get there.
I appreciate it.
That's awesome. And like, what would you say to maybe encourage more young people to get into engineering?
You know, I would say that a lot more of it seems very intimidating, right?
Yes.
And it really, you kind of think of stuff like this and it's like, oh, they must like totally know what they're doing.
Yeah.
And don't get me wrong, the people here are like incredibly smart, but also we're just figuring stuff out, right? And trying to kind of think of things. So, you know, for a long time, I just kind of assumed I wasn't like smart enough for this stuff. And I kind of have come to the realization that really, if you want to do it, you can. You know, it's just a matter of taking the initiative and making it happen, and it's really a blast. And
putting in the effort, and you're here doing it. That's awesome. What would you say about learning here at UTSA?
UTSA is great. I honestly wasn't sure that I was coming here, but it's a fantastic school. It's a good size. It's small enough that you can really get good attention from professors, you can know people really well, but it's big enough where you have a lot of resources.
Yeah.
And we've got some awesome facilities like this one, right? So it's a great school to go to. I highly recommend it for any high schoolers that are trying to fill out applications right now.
Yeah, come here.
Yes.
How is it working with that Dr. Combs guy? How is he really?
Dr. Combs guy? Oh, you know, I don't know if I should give my honest opinion here. No, Dr. Combs is great. He's super supportive. You know, he kind of is very good, I think, about understanding, like he was talking about earlier, the process sometimes isn't smooth and isn't easy. But he gives us the resources we need to do well, and the support we need to do well, and kind of lets us run with it. So it's really fun.
So if you guys enjoyed that video, please make sure to give this video a thumbs up, leave a comment for the algorithm, and subscribe to Ellie in Space if you haven't already. Can't wait to see you in the next video.